Okay, well, thank you everybody for joining again for the DOE ARC seminar series. Today, our speaker is Chen Wang from the University of Massachusetts Amherst. Chen is currently an assistant professor in the Department of Physics at the University of Massachusetts Amherst. His research focuses on new avenues to protect and to operate superconducting qubits on both the physical and logical level. The logical level work will be something that Chen talks about today. Chen graduated from Peking University in 2006 with a bachelor's degree, a bachelor's in science and physics, and Cornell University in 2012 with a PhD in physics. He worked at Yale as a postdoctoral associate before moving to UMass in 2016. Chen is also a recipient of the DOE Early Career Award and Young Investigator Award from AFOSR and ARO. And today he's here to talk about dissipative stabilization and error correction in a bosonic qubit. So with that, I'll stop sharing and you can go ahead and take it away.
All right. Yeah, thank you very much. Thank you, Greg, for the invitation and for the introduction. And it's a pleasure to meet you guys all over Zoom. And today I'm going to let me screen share first. And I hope you guys can all see the screen. I'm going to tell you about some of our experiments that we're doing in our lab with respect to dissipative stabilization and error correction for superconducting qubits, and in particular for bosonic qubits or interesting quantum states that are in the superconducting cavity. So the context of this, I think it's interesting to think about the role of dissipation in our everyday information technology, right? So when we talk about this quantum information science, we're mostly trying to really work with the unitary evolution of quantum states. And this is quite different from actually how we think about classical information. And there is actually a very essential role for dissipation in classical information technology. For example, you have all these bit arrays stored, let's say, in a magnetic hard drive. And you can see that the fact that we have dissipation in the system, it's very essential for the operation of the system, because whenever you have environmental noise that will agitate your information around, there is dissipation that puts you back in place. So it's this type of a kind of equilibrium that protects your information, and dissipation plays a very essential role that dumps the entropy and stabilizes classical information. So this entire mechanism is kind of absent in our usual way of thinking quantum dynamics in the system. So we like to think about this this question. Can we use dissipation to just do something that helps us with our quantum information processing paradigm? So the first question one can ask is, can a quantum superposition state live under dissipation? And there's actually a very trivial but kind of fascinating example to think about it, and this is elementary quantum mechanics, but I still find it fascinating, to think about it. So the standard weakly damped driven harmonic oscillator is actually such an example. If you have a pendulum, or you have an electrical circuit or electrical LC oscillator, or if you have an optical cavity, right? It's a harmonic oscillator system. You have some weak damping, and you can drive it maybe with close to resonance, but with some small detuning. You can write out your Hamiltonian like this. This is your oscillator Hamiltonian with a drive term, which oscillates close to the resonant frequency, but with a detuning on it. And your quantum dynamics would be described by a Hamiltonian as well as a dissipation operator. And in this case, the dissipation operator describes the damping of your oscillator. Which in an optical cavity language, or in a microwave cavity language, it's described by an annihilation operator that extracts a single quanta of excitations from your system. So you know the solution of this kind of quantum dynamics through a master equation is a coherent state. This is an expression of a coherent state. It's a coherent superposition of many photon number states. So here n represents the number of photons in the system. And we know this is the solution of the system. And you see that this is actually not a naive like a number states. It's actually a quantum superposition state. And we call this superposition state like a boring and quasi-classical because the dynamics all follow your standard like classical prediction for the most part, but it really is a quantum superposition state. And just to describe the kind of language here, we will describe these states. So we can use a phase space picture to represent the state. And if we think about the pendulum, there's x and the p. So this coherent state is represented by a kind of a minimum uncertainty packet that is like rotating around your x and p space. And usually we think about this in a rotating frame so that we're going to just call it in phase and quadrature component or real and imaginary axis. And we're going to say the steady state solution of this dynamics is a blob that is stationary in a rotating frame. And we're going to forget about this rotation in the rotating frame. It's just a blob that is stationary. So this is a trivial example of a driven and dissipative system that is stabilized into a quantum superposition state. And of course, there isn't really too much quantum information ideas you can really do out of this process. But more generally, if you can engineer interesting dissipation operator, in this case, if you have some kind of dissipation operator L, and in the system will relax to some steady state where this dissipation operator acting on your quantum state will return to itself, as well as you have some effective Hamiltonian that your system, the state is its eigenstate of. And more typically, if you want some kind of a target state, and if you have a dissipation operator and a Hamiltonian that satisfy this dark state condition, and also so that the dissipation operator will annihilate your wave function, as well as your state is an eigenstate of your Hamiltonian, then you will be reaching this steady state condition with your wave function. And this wave function could be an interesting quantum state you care. It could be a resource state, or it could be a manifold state. It could include your qubit of information. So anyway, to summarize, the point is that whether you can use dissipation to your advantage really hinges on whether you can create interesting quantum dissipation operator. And this kind of paradigm is coined with a term called quantum reservoir engineering from a few decades ago in the trapped ion context. So is there a question there?
I think it was just someone unmuted.
Okay, yeah, that's fine. Yeah, if you guys have questions, please feel free to interrupt. So there's actually many various ideas out there, experimental demonstrations of using quantum reservoir engineering. You can engineer different types of dissipation operator that will stabilize some interesting qubit superposition state, squeeze the state, Bell state. There are many different ways of producing interesting dissipation that will stabilize a specific non-trivial quantum state. And more recently, the more interesting direction we're going into is we ask this question: can we use reservoir engineering? We engineer some dissipation operator that will not just stabilize a state, but more than one state. Can we use the dissipation to confine your quantum dynamics into a 2D, 3D, or of a multidimensional system that can be interesting to do qubit encoding? So this is one interesting example. It's a simple extension of the oscillator stabilization. If you replace your Hamiltonian drive with two-photon drives, instead of A and A dagger, you have A square, A dagger square, and you replace your dissipation operator of A by A square, then you suddenly realize your steady state is composed of a plus alpha coherent state, a minus alpha coherent state, or any kind of a superposition state between them. So you've created two dark states with same energy. And now you can actually devise a logical qubit encoding that you can encode, you can use these two states as well as any type of superposition states of these two states would also be steady state of your driven dissipation process. Then you can use this kind of driven dissipation to confine your quantum state of a high dimensional space into this two-dimensional space. And this can be an interesting qubit to work with. And in this particular case, it generates a biased noise qubit that would exponentially suppress phase flip in this process, given reasonable physical parameters. So this kind of biased noise, we also called cat state qubit, because it's a superposition of multi-photon coherent state. It's called a cat qubit. In this case, it's also called like a two-component cat qubit. That is of intense research interest lately. There's obviously a major downside of this encoding is that the bit flip is not corrected, which is induced by single photon loss in an oscillator, and this is an uncorrectable error. So in this talk, I'm going to tell you sort of further steps and extensions of these dissipation engineering ideas. One is that now we talked about two-photon drive and dissipation in a single cavity. One new aspect is how about let's build out our tools of reservoir engineering in two-cavity Hilbert space. So I'm going to tell you about our experimental realization of a pair-photon driven dissipation process in two cavities, as well as the production of the so-called pair-coherent state. And the other is autonomous quantum error correction, that using driven dissipation to combat and to erase single photon loss errors in a single cavity cat qubit. So this is going to be the second topic of this talk. So first, let's talk about this two cavity process. So this is you can kind of think about a theoretical extension of this idea of stabilizing a coherent state. If you have a single photon drive, single photon loss, detuning Hamiltonian, you know this is your steady state in a single harmonic oscillator. And if you extend this towards two-photon drive, two-photon loss, we know that the steady state we can write it as with an amplitude alpha and with a photon number parity operator eigenstate of parity of +1 or -1. Which represents the two possible eigenstates. Actually, it's a degenerate to the a manifold of cat states that can be represented by this block sphere. That's your plus minus alpha, and these are the plus and minus superposition states of plus alpha and minus alpha. So this is a single mode two-photon driven dissipation process, and if we think about having two harmonic oscillators, and if we think about pair-photon drive and pair-photon dissipation together with possible like a cross-Kerr Hamiltonian, then the steady state turns out to be the so-called pair-coherent state. And the pair-coherent state is also described by an amplitude, just like coherent state or cat state. And it's also described by another quantum number that's called photon number difference. That describes the photon number, how different the two cavity photon numbers are. And it actually stabilizes a manifold of states, which all has the same amplitude, but they have same complex amplitude, but have different photon number difference. So this experiment, we show how to generate this new dissipator, and as a result, we characterize this new class of quantum states. So just to write this out a little bit, this is the coherent state formalism you're familiar with. Alpha is the complex amplitude, and here it's a superposition state of many photon number states. And extending this to two oscillators, this is called a pair-coherent state. It's described by two quantum numbers. This is a complex amplitude, And this delta describes the photon number difference. It's the same kind of Poisson-like distribution, and its underlying states are composed of Fock state combinations in the two cavities. So it may look a little bit complicated, but just to give you an example, if delta equals to 1, that means photon number difference is 0. Then this is simply a superposition of 0, 0, 1, 1, 2, 2, 3, 3, so on and so forth with a Poisson-like distribution. So the property of the pair-coherent state is that it's an eigenstate of the pair-photon annihilation operator. Ring a bell with your coherent state, right? Coherent state is the eigenstate of the photon annihilation operator. So this is the eigenstate of the pair-photon annihilation operator. It's also the eigenstate of the photon number difference operator. This is simply just computing the photon number difference between the two cavities. So this PCS state, it's kind of interesting because it's a first example of what we know as a logical qubit encoding that has the minimum number of dimension, or degree of freedom that allows autonomously corrected logical qubit. So this is the pair coherent state. So there is this so-called pair-cat encoding or pair-cat qubit, where you would put a logical 0 onto a pair coherent state, and you put logical 1 onto a pair coherent state of the opposite complex amplitude. So think about this as encoding it as into the same of single cavity coherent state. You have alpha and you have minus alpha. You use these as your logical encoding. And for example, in this case, your 0 logical will be 0, 0, 1, 1, 2, 2, 3, 3. 1 would be 0, 0, minus 1, 1, plus 2, 2, minus 3, 3, so on and so forth. So this kind of a logical qubit allows you to do reservoir engineering. You can dissipatively stabilize the amplitude and phase of this cat state manifold by doing a complex dissipation operator like this. And also, it allowed you to do autonomous correction of photon loss by kind of destabilizing some photon number difference states while stabilizing some particular photon number difference. So this is actually still a pretty far out goal to implement. So this experiment I'm going to show you is sort of the first step of engineering cross-cavity dissipation, as well as perform measurements of the photon number difference in this kind of a system. So this is our experimental device. Here, what you're seeing is a superconducting cavity. It has this is where the cavity is. It has two posts. This is made out of aluminum, and these two posts, the heights more or less determine the frequency of this microwave cavity mode frequencies. And there is a chip that is inserted in a tunnel somewhere in this region. You can see the chip sticks out into this cavity a little bit. That's where a Josephson-based superconducting transmon is located. So it's represented by this pink symbol there. So the system is composed of two storage cavities. That's where the pair coherent state will be stored in. This superconducting, sort of like a 2 or 3 level system, a transmon. That's what you usually call a superconducting qubit. In this experiment, we're going to use this as the ancilla to operate this bosonic harmonic oscillators. And then there will be another oscillator that is coupled to the transmon, which we use. This is a low Q resonator that we're going to use it as the resource of dissipation. It's the entropy dump, and it's also used for reading out the transmon. So the system Hamiltonian is just a bunch of oscillator terms. If we ignore this part, just to focus on the two cavity and the transmon, so it gives us oscillator terms, the qubit term, as well as the dispersive terms. So these dispersive terms tell you that the cavity frequency shifts when the transmon is in excited state. Or in other words, another way to think about it is the transmon frequency shifts for every additional photons in the microwave cavities. So this is the device picture we have. And in order to engineer this two-photon driven dissipation process, we would drive the system with two tones. One is a simple drive on, one is a four-way mixing drive at this frequency, where it activates a four-way, it activates this process that it would convert a photon in this readout resonator or reservoir resonator into pairs of photons in cavity A and cavity B. And the reverse process is also true. This is a bidirectional four-way mixing process as long as you hit this frequency condition. And the other drive is we simply put a weak drive on linear drive onto this reservoir resonator. So the process, you can see it from this kind of a ladder diagram. There is four-way mixing that annihilates pairs of photons in A and B while adding a photon in the reservoir. So these numbers are A, B, and the reservoir. So this is the four-way mixing drives. It connects these levels. And also we put a small drive that is connecting the neighboring levels between 0 and 1. And also the system is lossy because the reservoir has decay rates. So this will be sort of the ladder diagram to think about. And because the reservoir is very lossy, you can do adiabatic elimination of these states out of the picture. And the result would be that you create this ladder that is connecting 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and so on and so forth. And because there's both drive and there's dissipation, so you end up doing a bunch of math and you realize your steady state is this so-called pair-coherent state. So experimentally, we do this. We can apply these two drives. One is this reservoir drive, and the other is this four-way mixing tone. If we apply these drives for some amount of time that is sufficiently long, we can analyze the state of the two cavities by doing a spectroscopy measurement of the transmon. As I said, the transmon is dispersively coupled to the two cavities. So just looking at how much frequency shift your transmon experience, you can figure out how many cavity photons you have in the system. So vacuum would correspond to no frequency shift. And if you have more and more photons, you have more and more frequency shift. And because we know what the chi exactly is, we can look at the transmon spectrum and figure out what is the photon number populations. And in this case, we get a 0, 0, 1, 1, 2, 2, 3, 3, 4, 4 state. We don't know if it's a superposition yet, but we will analyze that later by measuring quantum coherence. So these are measurements in the time domain so that we can actually analyze the stabilization dynamics. So in this case, we would turn on the pump tone for some varying amount of time. So this is the stabilization tone, how long the stabilization tone is applied. And we can monitor the population or the probability of the two cavities in 0, 0, 1, 1, 2, 2, 3, 3, and 4, 4 states. And you can see that it starts in vacuum because 0, 0 is at close to 1. All the other states are unoccupied. Eventually, it stabilizes towards some kind of probability distribution. There is some oscillatory behavior because this is sort of like an underdamped oscillator. The effective two-photon loss is not extremely strong. And we do these experiments and have a full calibration of the two-photon dissipation rate, the two-photon drive rate, and these rates are substantially larger than the single-photon decay rate in the two cavities. So this allows us to get a reasonably good description of the system in terms of a cross-cavity two-photon drive and dissipation process. So yeah, we can also, so in this experiment, the reason that it converges to the 0, 0, 1, 1, 2, 2, 3, 3, 4, 4 state is because we start in a vacuum, and vacuum has this photon number difference of 0. So that's why it goes into this equal photon number PCS state. So if we start our cavities in a 0, 1 or 1, 0 state, which we can prepare with this protocol called the snap gate, we can prepare single photon Fock state in either of the cavities. Then if we turn on this stabilization drive, this dissipation process, we analyze the state, we can see that it converges into this delta equals 1 state or this delta equals -1 state. So this shows you that the same stabilization process is capable of stabilizing different photon number difference states, but they all have about the same amplitudes. And this, of course, only shows you population distribution. So we actually did a lot of experiments trying to analyze the quantum coherence in this pretty large Hilbert space. So this is the one form of characterization. I'm not going to go into too much detail, but this is called a joint Wigner tomography. So the idea is this is called the Wigner function, just like a single cavity Wigner function. It's plotting a quasi-probability distribution in the phase space. So in this case, it's a 4-dimensional phase space. So it's a lot of data to take to measure this. And these are the experimental results for a 2-dimensional cuts, which is like along the real axis of cavity 1 and the real axis of cavity 2, cavity A and cavity B. So this interference fringe tells you that there is coherence in the system. It's not as strong as the ideal case, but all the phenomena that we see corresponds to the PCS superposition. And if we do the +1 or -1 different photon number different states, we get opposite contrast of fringes. And this blue fringe tells you the photon number difference is +/-1. And this Wigner negativity is also a kind of a definitive proof of non-classicality in this kind of quantum states. And in fact, using these Wigner tomography, if you know, like doing complex multidimensional quantum state tomography, it's extremely challenging, and there's additional experimental complications in this. I'm not going to go into details, but in this experiment, we spent a lot of effort trying to figure out what the density matrix actually look like. So there's an interesting procedure that we introduced called quantum subspace tomography. Essentially, the goal is to directly measurement the density matrix element by element. So this is the type of density matrix we construct, and this is the delta equals 0, where the photon numbers are equal to each other between the two cavities. And the population measurement tells you all of the diagonal elements. And the off-diagonal elements, you can infer that from the Wigner fringes, but in fact, the reconstruction is quite hard. So there's a procedure we're able to pick out individual pairs of photon numbers and produce and perform a Ramsey interference measurement between the two. And this actually allows us to figure out exactly how coherent each pairs of photon, each of pairs of these constituent states are. So this was we did a lot of quantitative analysis in this experiment to see how good this PCS state is. And the spoiler is the PCS fidelity is not high, and there's a lot of imperfections that would need to be improved in the future. So now I'm going to move on and talk about another topic, which is a single cavity experiment, but we're trying to stabilize not a complex amplitude of the coherent state in the system, but we want to correct photon jump errors. So this is a simple picture as thinking about cat state or pair-coherent state. If you stabilize your system in a manifold of cat states, you stabilize like average energy in the system. You're still subject to single photon loss, which is going to bring you hop between even parity states and odd parity states. That's what single photon loss does to you. And your two-photon protection is not going to help you against such single photon loss process. And similar in the PCS stabilization, if you perform two-photon drive or four-photon drive, single photon loss in cavity A or cavity B is going to change this eigenvalue of photon number difference. And you will need to figure out additional stabilization scheme to stabilize those. So this is our experiment, our data from our PCS state measurements. As time goes on, the amplitude and phase are stabilized, but the photon number difference, initially, if you start from 0, you're going to see the population in ±1 state will just continue to grow because the scheme is not helping you with single photon loss, which is, by the way, usually the dominant physical decoherence mechanism in these superconducting cavities. So if you ask the theorists, how do you produce some kind of passive protection scheme to stabilize the photon number parity for a cat state or stabilize the photon number difference for pairs of cavity? They will tell you you want to build nice Hamiltonian that is proportional to you build some Hamiltonian, you bring in an ancilla, we call that sigma z. You want the Hamiltonian that is proportional to the parity operator or proportional to the photon number difference operator. So this is easier to build than that, which is why this PCS has kind of the pair-coherent, the pair-cat code has its appeal. So we are going to tell you about an experiment that we're actually kind of to go around with this condition and to realize a kind of stabilization of the photon number parity operator. So just to introduce this single cavity encoding. So I talked about this two-component cat state encoding. There is actually another slightly more elaborate encoding called the four-component cat code. So in this case, you think about a negative superposition state of your alpha and the minus alpha state, and you can use this as your logical X state. And instead of using the plus superposition, which will have the opposite parity as your other logical state, you can use the same minus state, but with a 90-degree phase shift for your cat state. Use this state as your minus X state. You can check that if your alpha is large enough, these two states are completely orthogonal to each other. And these two states also share photon number parity. They are both odd parity. They are only composed of 1, 3, 5, 7 photon numbers and so on. So you build up your logical block sphere, looks like this, and your north pole would be 1 mod 4 states, and your south pole would be 3 mod 4 states. So this is actually the original cat code, which allows you to correct for single photon loss. The reason is that if you have a photon loss in this kind of a logical encoding, then all your odd photon numbers will be converted to even photon numbers, because obviously 1 goes to 0 and 5 goes to 4 and so on. Also, because of the coherent state property, you can see that alpha minus alpha will just be flipped into alpha plus minus alpha without really changing the total energy in the system. So this is the property of coherent state. So you can build out this cat state manifold and give you this nice property that a single photon loss is going to keep the structure of the block sphere while having a parity flip. And you can understand the parity in our Wigner function language by looking at the center pixel of the Wigner function. Blue means odd parity, red means even parity. The same thing as the joint parity function I showed you for two cavities. So errors can be tracked by performing repetitive quantum non-demolition measurements of photon number parity if you want to do active quantum error correction in this system, which is exactly what was done now quite a few years ago. And this experiment using this four-component cat state encoding showed an improvement of a logical qubit lifetime over the physical counterparts. And it takes a very complicated decision tree FPGA programming to keep tracking of the photon number parity in the system and make decisions of how to operate the ancillas and apply different pulses on the fly and analyze what to do with the logical qubit to keep it alive. So doing this kind of active quantum error correction is very resource intensive. And this is exactly the reason why we like to think about, can we use dissipation to simplify the situation, we want to think about how can we apply passive protection to this kind of a physically encoded logical qubits. So can we apply time-independent dissipation to replace this kind of active correction diagram? And this dissipation operator L, it has to say this message. Whenever the parity flips, please flip it back with the right phase, please. Okay, so the way to think about this would be if you start with a logical block sphere where you have 1 mod 4 and 3 mod 4 states, then if a photon loss error happens, it's going to shift your information into an error block sphere, which is an equally good block sphere, but it's just a difference. It's this idea of a quantum error correction, right? It goes to 0 mod 4 and 2 mod 4. So if you can make this C to be a stable block sphere and make this E block sphere to be an unstable block sphere, and also your dissipation would always be orthogonal to the block sphere surface, and it just maps these states isomorphically to the blue block sphere, then that will be the dissipation operator you want. It doesn't necessarily have the nice form of A square or AB, but that's some operator you can try to write down. So the way to think about this dissipation is that if you can engineer some dissipation that projects 0 to 1, 2 to 3, 4 to 5, 6 to 7, then you more or less will be able to accomplish this goal. And because we don't want to unnecessarily put more energy into the system, generally we don't work with a huge alpha. So you can, in this experiment, we would truncate out all the number states above 8, and we would use a truncated version of this 4-component CAD code, which we call T4C. So an important point, so if we can produce this kind of dissipation, and we make sure these are not 4 separate dissipation paths, but they are like a superposition of these 4 projection operator, then this type of a dissipation operator would allow us to perform a quantum error correction against the single photon loss. So this is how it works. And I'm going to tell you how you can make these 4 terms to be superposed with each other. And this is a very similar device. And it has only 1 storage cavity and the transmon and the readout resonator there. So I'm going to represent these states. So the blue states are the logical, the good odd parity states, and the red states are even states. These are the error states. So the first number represents photon numbers in the storage cavity. And the second one represents the transmon in ground state. And the third one represents the readout resonator in vacuum, in ground state. This is a lossy resonator, so it's almost always in vacuum. And imagine if your system starts in 1 photon fog state and the photon loss has occurred, so you get to vacuum. Imagine if you put a coherent drive on your transmon, it flips G to E. This is a bidirectional process, obviously. And then you're going to connect these 2 energy levels. And importantly, this transition is not driven because of dispersive shift. Your transmon frequency depends on the cavity photon number. So you only drive this transition, but not this one, as long as your rate is weak enough. Then you put a 4-way mixing process that de-excite the transmon and put 1 excitation in storage and 1 excitation in the reservoir. Now, this is a process that you can also do. And now, because this reservoir is lossy, it's going to lose a photon, and that's going to lock you back into the good state. So this will become a dissipative process that adds a photon into the vacuum. And now, imagine you put a comb of tones, like a four drive tones, to excite your transmon, conditioned on your cavity being 0, 2, 4, and 6, and you put 4 tones there to connect these levels. Then you will be able to destabilize all your red states and lock them back respectively to the blue states. And more importantly, these four tones have all slightly different frequencies. And these four tones all have slightly different frequencies, but the frequency difference compensate each other. So all these four tones, they emit these four emission processes. They all correspond to the reservoir losing a photon, emitting a photon into the transmission line. The transmission line, a hypothetical detector would not be able to tell which path the system has gone through because these four frequencies are equal. So this allows us to erase the which path information, and therefore the original superposition states between these four levels are going to preserve through this entire process. So with this diagram, adding these drive tones together with these dissipation of the reservoir would allow us to implement this type of dissipation operator that we called parity recovery through single photon addition. Okay, so let's show some data, and this is the first step that we're going to show. We're going to show dissipative addition of a single photon to the vacuum state. So we initialize in zero state and we pump on the system, and then we analyze it with a transmon spectroscopy. That's actually the same type of experiment I showed you earlier. So the x-axis is the transmon spectroscopy, transmon frequency, and y-axis is time. So you see you start in vacuum, and after some time, the transmon frequency hops to minus chi, one-time dispersive shift. So that tells you the transmon has jumped from the cavity has jumped from vacuum to one photon fog state. So you can see that after 25 microseconds, the cavity gained a photon. It's not a coherent oscillation process. Also, it does not climb up the ladder as we want, as we design. So one photon state is more or less stable for quite a long time. And we can also show even to odd conversion. So in this case, we prepared a 0, 2, 4, 6 superposition state. We turned on all 8 drive tones, and this allows the system to dissipatively converge to this 1, 3, 5, 7 states. And in this case, we used some optimal control numerical pulses to prepare this initial state, which is going to be used a lot in this experiment. And this experiment, once again, we perform a time domain measurement where we pump for a variable amount of time and analyze the system. You see that the 0 state will converge onto a 1 state after some 10 microsecond time scale. And if we start in 2 states, it converges to 3. If we start from 4, it converges to 5. And if we start from 6, it converges to 7. So the population is differ from 1 in the end. So these are error states that it either leaks down towards the ladder, or it's just in some equilibrium that will remain in the wrong states. So this is because the higher the photon number is, the more single photon loss in the system is happening, so that the correction is no longer as strong as it's needed for high fidelity convergence. And we can extract the pump rates there. In fact, we use this type of experiments to calibrate the 8 pumps in order to make sure all of the conversion rates are equal across all the paths, which is also important to make sure we don't leak information. And this experiment, of course, don't show you quantum coherence. So to calibrate, to show coherence, we prepare these pairwise superposition states of even states, and we turn on the pump tones. And after a while, you see they all get converged into odd parity states. You can see the center pixel changed from red to blue. This tells you the parity of the system. And we did, for single cavity, Wigner function reconstructing to density matrix is much easier. So we get the numbers out, and we see about like 2/3 efficiency for the correction. So for quantum error correction, of course, ultimately you need like a better quality, but if you can catch like 1 error out of 3, that's still a reasonably successful correction in this case. That's why we can put this passive correction into use to test it on actual logical qubits So in this case, we prepare the 6 cardinal states of the block sphere. So these are 6 odd parity superposition states that represent the six cardinal points of the logical block sphere. And if we leave these cat states evolve for free, and after some amount of time, you can see that the interference fringes has disappeared and your logical information has mostly lost or lost to a very significant degree. But if we apply the drive tones, apply these passive protection tones for the same amount of time with this autonomous quantum error correction drives, you see the Wigner function. From the Wigner function, the pattern is preserved much better. We can be more quantitative and perform this experiment. So if we put our logical qubit encoded into these cavity states, and we simply wait as the free evolution I just showed you, and after some amount of time, instead of measuring the Wigner function, we can decode it, map it back to the transmon, and then do a transmon tomography to figure out how much information is left. You can see that the encoded logical qubit would decay over 130 microseconds. So the cavity lifetime is roughly 400, and this is less than that because you're using multiple photons to encode your information, and therefore it makes you more susceptible to error. And if we, instead of just wait, we put on our pump tones on, you can see that we get a logical lifetime of about 288 microseconds. So that's roughly a factor of 2 improvement from the uncorrected state. So in the system, there's a different way of encoding. If you put your logical qubit in the Fock state superposition of 0 and 1, you can actually get slightly better performance of 440. So this is really actually a very tough enemy to beat in quantum error correction. Every time, in order to make your system better by doing error correction, you always have to expand your Hilbert space and contend with stronger decay channels. And you always have to pay a big overhead, and then you have to overcome this overhead. This is the so-called quantum error correction break-even game. So in this case, we're unable to reach break-even, and we're able to correct the photon loss fairly well, but the system also has some heating effects, and also the transmon has both spontaneous thermal excitation and like a uncorrectable T1 decay process on the ancilla, which is limiting the system performance. In general, we need better thermalization on the ancilla to reach break even. But this 2.2 times is the punchline that we show that we can use dissipation to perform quantum error correction against the single photon loss error in the system. So in the future, we hope that we're going to work on single cavity encoding a little bit more before going to the pair cat states. So for photon loss error, we use this parity recovery operator. We can correct it, but then this cat size will spread a little bit, and this cat state will also have some phase drift, which is the remaining error. These can be corrected through a 4-photon driven dissipation process that we're going to work on. And this will allow us to produce first-order protected bosonic qubits within the single cavity. And to put this in a bigger landscape, quantum reservoir engineering, as I've introduced it to you, I feel is a very interesting and could be powerful concept in doing quantum engineering. And in addition to lots of literature on preparing and stabilizing a resource state, I've showed you that it's useful for confining or stabilize a manifold of states in the context of a 2-cavity generation and stabilization of pair-coherent states. And I also showed you this autonomous QEC of photon loss error. And to take one step forward, you can also think about using dissipation engineering to perform some quantum operation of your system. So this is an example you can think about doing autonomous quantum state transfer from one Hilbert subspace to another Hilbert subspace by using dissipation engineering. This is a theoretical kind of analysis we did. And furthermore, you can even think about dissipative quantum gates or autonomously corrected quantum gates. These are further steps of thinking of how to use dissipation to help stabilize your quantum operations. So yeah, I will just to acknowledge my students, and these experiments are carried out by my grad students, Jeff, Shudi, and Sean, as well as a previous postdoc. And this is also done in collaboration with the Northwestern University with Jens Koch, as well as Liang Jiang in the other project. And I have open positions for postdocs and grad students. And if you have people interested in, please let me know. And I'll be happy to take questions.
Thanks, Chen, for the nice talk. Any questions for the speaker?
I have a question. Thanks for the talk. So looking further ahead to the point of doing 2-qubit gates, say using cat qubits, would the idea be to use sort of a common transmon to couple two different cat qubits somehow and use that to control for 2-qubit gates? Or how would you go about doing that?
Yes, so there are different there are different possibilities there. So the most straightforward idea seems to be using a transmon as the ancilla that is simultaneously coupled to the 2 qubits. Then there's fourth order nonlinearity that allows you to do forward mixing, and in general, all the logical 2-qubit gates are possible. So it has its limitations. Mostly, the question is. How much can you keep the transmon grounded and not incur not have the decoherence problems of your transmon to propagate into as uncorrectable errors in your gate? That is quite a challenging problem. So far it turns out if you use a transmon and to do 2-qubit gates, 2 bosonic cat qubit gates, it's generally slow, so it's not competitive against the say 2 transmon gates yet. So there are different ideas. So one direction people really look into is to not use the transmon as the ancilla, but use a different type of circuit as ancilla. And those things generally, because it's after all, it's just a Josephson junctions and the inductors and capacitors, and you lay out things and you design Hamiltonian, lots of play there. But those things tend to be more complex and harder to master than transmons. But you can have things that are not like a qubit, but that really look more like a tunable coupler type of things. So they don't directly participate in excitations, but they only modulate some kind of interaction between the cavities. So these kind of strategies seems would allow you to get better performance. And then there are also ways to think about these bosonic qubits. In this case, my bosonic qubits are big cavities. They by themselves don't have Josephson junction with it. There are also circuits that are bosonic-like, but they do have some nonlinearity, including the Josephson junction with it. Then you can potentially not even have an ancilla, but you just pump your bosonic qubit in some way, and that will stimulate interaction. That's also another direction people go about. But those kind of bosonic qubits should generally have a little bit worse starting point in terms of the cavity lifetime to begin with. But there's also interesting advantages as well.
Cool, thanks.
Any other questions? So I have perhaps I guess maybe a stupid question. So you talked at the end about the idea of doing dissipative gates. So I guess in that case, these are logical gates, and so in order to do this, you have to. I guess in order to do this fault tolerantly, right, you have to think about being able to satisfy thresholds. Is there any thoughts? I guess I don't know much about the work in this area on the theory end. Is there any thoughts of or notions of threshold theorems here, and how and how one would what sort of I guess physical error rates that one would need in order to ensure that these dissipation processes are working correctly, if that makes sense.
Yeah, I think it definitely makes sense. So the thing, the funny business of what is a logical and what is a physical here, I think is a little bit blurred. So I would say for the type of logical we work with, it's not logical in the sense that there is a clear way to scale it to 10 to the minus 18 like error rates, right? So what we mean by logical here is that it is using a higher dimensional Hilbert space to encode your information so that you kind of so that you kind of separate your you have your information to be protected to some degree against the most naive physical errors. So in that sense, if we want to have this encoded like logical gates, so the idea is that you add dissipation so that these physical errors that will happen during the logical operation will be kind of stabilized and damped by your dissipation. And the goal is to kind of deliver a higher gate fidelity than you would have had in a system that is subject to exposure to the direct physical error. So now, after that, I would say you can think about this at the simple way to use this is to use this as your building block for the next level of whatever software-based error correction. Then if you do that, then all the threshold theorem applies, and this is simply just a goal. Think about this as potentially an intermediary step that brings your 99% fidelity gate into a 4-9 gate, if it's possible. I mean, it's obvious. It's not obvious how one can do that. Has had that idea yet. But then you can build additional layers on top of that, concatenate with some of the standard fault tolerant architecture to further scale up. And then, of course, there's also more purely bosonic approach to think about these codes. Certainly, if you, in this CAT code, if you want to protect against, say, multiple photon loss errors, there's a simple strategy. Instead of going like a mod 2 parity, you can go with mod 3 parity. Then that's going to protect you from two-photon loss, for example. That's one analogy of like of a building code space, building like a code distance in terms of quantum error correction. But if you want to protect against all other sorts of error and all possible like ancilla errors, and also when you do logical operations, there's also control errors. So these different things all needs to be protected. So it's a sort of a big open research, and people think about what kind of ancilla would be fault tolerant. Would allow you to do fault tolerant operations and so on and so forth. Yeah.
Cool. All right. Well, thank you. I guess thank you for the very in-depth answer. I appreciate that. Okay, well, we're out of time here, so I want to respect everyone's time. Chen, thank you again for the very nice talk. And I guess we will see everybody next month for the next ARC seminar. Okay. Thank you, everyone. See you.
Okay, yeah, thank you. Thank you, Greg.
Thank you.